In this video, we're just going to review some of the representation concepts that we covered in class last time. We're going to be using a 3-bit example, so we're going to be using a representation that's made up of 3 bits. Each bit can be either a 1 or a 0, and so when we have 3 bits, we have a fixed number of combinations of 1s and 0s that we can use to represent other values. And in particular, I'm going to look at how I can divide those bits different ways to represent integers, different types of integers. I'm going to start out by looking at unsigned integers. So if I want to represent unsigned integers, I want to represent only positive values. And so my question is, what are the largest and smallest values I can represent using 3 bits? Well, first I can start and I can say, well, what are all the different combinations of 3 bits that I have? These are all the different ways that I can assign a unique combination of 1 and 0 to each of the bits in a 3-bit representation. So when we're representing only positive numbers, we take the arrangement of all zeros, so in 3-bit that's 0, 0, 0, and we use it to represent the decimal value 0. And then we take increasing binary values and we assign them increasing decimal values. Which is pretty straightforward. So it means that if I want to know what the smallest value I can represent is, I look for the combination of 3 zeros, so all of the bits are 0, right? And I use that to be equivalent of decimal 0. It's the smallest unsigned value that I can represent in 3 bits. If I want to know what the largest value I can represent is, I look for the combination where each bit is a 1. So I'm contributing the maximum weight because I'm contributing the weight of each digit in my binary number. So in 3-bit, that's 111, which is equivalent to decimal 7. In class, we also looked at how we could extract a sort of general equation or general pattern. We said that in an unsigned representation, right, the smallest decimal integer we're going to be able to represent is always going to be 0. The largest number that we're going to be able to represent can be written out as 2 to the n minus 1, where n is the number of bits in the representation. Here I have a 3-bit representation. 2 to the 3rd is 8, minus 1 is 7, and 7 is in fact the largest number that I can represent in an unsigned 3-bit representation. So it gets a little trickier though when we want to represent signed numbers, so where the integer can be positive or negative. Again, if we're using 3 bits, we still have the same 8 combinations of 1s and 0s. Right? It's just now, instead of being able to use all of them to represent exclusively positive values, I need to divide my range up and use some of those combinations of bits to represent positive values and some to represent negative. We said in class that we would take the representations that started with 0 and use them to represent the positive range, and we would take all the combinations that started with 1 and use them to represent the negative range. And the convention that we're going to use is called 2's complement. Okay, so now I want to figure out, well, what are the largest and smallest values that I can represent using signed 2's complement representation? Just to keep things from getting too confusing, we're still going to reserve the combination that's all zeros, 0, 0, 0, to be the equivalent of decimal 0. And in fact, all of the numbers that are positive, so have that leading 0 indicating that they're positive numbers, are going to have the same representation, either signed or unsigned. So now what we need to do is we need to look at how we can assign decimal equivalents to the negative representations, so all the ones that start with 1. Let's look in particular at this arrangement of bits down here, 1, 1, 1. So in unsigned, this was positive 7, but it's going to have a different equivalent in signed 2's complement representation. Let's remind ourselves how we get the decimal equivalent of a 2's complement binary number. So the first thing we do is we need to make sure we know the number of bits in our representation. This is really important. And here we're using a 3-bit representation. We need to make sure that our number fills all of the bits. Again, because we'll be flipping bits, we need to make sure that each bit has a value to begin with, so we know what to convert it to. Also, that leading bit gives us some sign information, so we want to make sure that the leading bit is there. The next step is to flip all of the bits, so the 1s become 0s. Had there been any 0s, they would have become 1. Then we add 1. And so now we have a number that we can convert from binary to decimal, and then when we read the result, we'll just put a negative in front of it because we know that this should be a negative decimal number because we started with a leading 1 in our binary representation. So I would just convert this result here from binary to decimal using the same strategy we use for any number, I would say, okay, well, I have a 1 here and the 2 to the 0 spot. 2 to the 0 is 1. 1 times 1 is 1. None of the other places contribute anything to the value of this number. So 111 in 3-bit 2's complement is equivalent to -1 in base 10. So I can go back to my chart and I can say, okay, well, 111 is actually going to be equivalent to -1 in decimal. Right? And then I can do the same thing to fill in the other values in my chart. So now I can see that I can represent a smaller range in the positive numbers than I could in unsigned, which makes sense. Before I was using all 8 combinations of bits to represent only positive numbers. Now I can only use half of them to represent positive numbers. But what I've gained is the ability to represent some numbers in the negative range as well. So I can go back to my original question, what are the largest and smallest values I can represent? Well, the smallest value that I can represent is -4. And the largest value that I can represent is equivalent of decimal 3. Well, as we mentioned in class, we'll always be able to represent one more value in the negative side of things than in the positive, because one of the arrangements of bits that would otherwise be positive, because it has a leading 0, is the combination that's all zeros, which we've reserved to represent decimal 0. So always be able to represent one more number in the negative direction than we can in the positive direction, which is why we can only represent up to +3, but we can represent to -4.